All right, we're about to dive into a geometric puzzle that, believe it or not, hides in plain sight, and it's all centered around one of the most familiar shapes in math. You guessed it, the parabola.
Okay, so let's just jump right in with a question. If I gave you any 3 random points on a graph, just floating in space, how many different parabolas could you draw that pass perfectly through all of them? Seriously, take a second. What's your gut feeling tell you?
So if you said 1, you are definitely not alone. That's what almost everyone thinks. But the actual answer? Well, it's pretty mind-blowing. It's infinite. Yep, infinite. And by the end of this, you're going to see exactly how that's even possible.
Okay, so to solve this little puzzle, they have to go back to basics. Like, really back to basics. What even is a parabola? I mean, yeah, we see them in graphs all the time, but its true identity? That comes from pure geometry.
So here's the official geometric definition. A parabola is basically the set of all points that are the exact same distance from one special point, called the focus, and one special line called the directrix. You know? Every single point on that curve has to follow that one rule, and that precise relationship is what carves out its unique, smooth shape.
Now, that geometric definition is its, true identity. But let's be honest, most of us know the parabola from algebra class, right? It's that classic U-shape that pops up when you graph a quadratic function. That old friend y equals ax squared plus bx plus c.
So how do we get from the one parabola we all picture in our heads to this infinite reality? Well, the bridge between those two ideas is a single, really elegant concept: the axis of symmetry. This, right here, is the secret key that unlocks the whole puzzle.
The easiest way to think about the axis of symmetry is to just imagine a fold line. It's this perfect line that cuts the parabola right down the middle so that both halves are exact mirror images of each other. If you could literally fold the paper along that line, the two sides of the curve would land perfectly on top of one another. And here's the most important part. That axis of symmetry always passes through the parabola's most extreme point. We call that the vertex. It's either the absolute lowest point of the U if the parabola opens up, or the absolute highest point if it opens down.
Okay, so how do we actually find this critical line? Well, there's a pretty famous formula for it, but look, instead of just memorizing it like we did in school, let's actually understand why it works. It's way simpler than you might think.
And here it is. The formula is x equals negative b divided by 2a. And yeah, that's the same a and b from our standard quadratic equation. This little thing pinpoints the exact x-coordinate of that line of symmetry. Pretty neat.
So here's where it comes from. First off, you can totally ignore the c at the end of the equation, because that just moves the parabola up and down. It doesn't shift it left or right. So we look at ax squared plus bx and find where it hits 0. That gives us two x-intercepts. One is at x equals 0, and the other is at x equals negative b over a. Now, since the axis of symmetry has to be exactly in the middle of those 2 points, what do? We just find the average. And the average of 0 and negative b over a is just negative b over 2a. See? It's not some magic formula, it's just finding the midpoint.
And the really cool thing is, this idea of finding the midpoint works no matter what form the equation is in. For the standard form, yeah, we use x equals negative b over 2a. But if you have it in factored form, you just average the 2 roots. And if it's in vertex form, it's even easier. The axis of symmetry is just staring you in the face. It's x equals h. All right, deep breath. We've defined what a parabola really is, and we've got a solid handle on its axis of symmetry. So now, armed with all this new knowledge, let's circle back and finally solve that mystery from the beginning. This quote from a Reddit discussion really just hits the nail on the head. The absolute key word here is function. There is only one parabolic function that can go through 3 points. But, and this is the big but, a function isn't the only type of parabola out there.
See, the parabolas we're all used to from school are functions. And to be a function, it has to pass the vertical line test, right? For that to happen, its axis of symmetry must be perfectly vertical. That's the one single familiar parabola we all imagine.
But that leads us to the final game-changing question. What happens if that axis of symmetry isn't vertical? What if we could just tilt it, rotate it?
And boom, there's our answer. As soon as you tilt the axis of symmetry, you're also tilting the entire geometric setup. The focus and the directrix go with it. So for every single possible angle you can imagine, you create a whole new focus and directrix pair. And each one defines a brand new, unique parabola that still passes through those exact same 3 points. Since there are infinite angles to choose from, there are infinite parabolas. They might not be functions anymore, but they are all absolutely real geometric parabolas.
And hey, for anyone who's curious and wants a little peek behind the curtain at the more advanced math, this is the general equation that can describe every single possible parabola, including all of those tilted ones. Don't worry, you don't need to memorize it, just cool to see that this is the master formula that governs that entire infinite family of curves.
So think about that. We started with the shape we all thought we knew, and we found an entire infinite world hiding inside of it. And we did it all just by understanding and then, well, by challenging a single rule, the idea that the axis of symmetry had to be vertical. It really leaves you with a final thought, doesn't it? What other simple rules in math or even in science that we just take for granted might actually be the keys to unlocking a whole universe of hidden complexity? Something to think about. Thanks for joining me on this one.